Welcome to Dreaming Through Knowledge. Tonight, we embark on a journey into the most fundamental, the most mysterious, and the most beautiful phenomenon in the universe. We are going to explore the thing that allows you to see the world, the force that feeds the plants, the speed that sets the limit for reality itself. We are going to tell the story of light. Without it, the universe would be a cold, invisible tomb. It is the messenger of the cosmos. It brings us news of stars that died millions of years ago. It paints the colors of the sunset. It warms the skin of the earth. But what is it? Is it a wave? Is it a particle? Is it pure energy? To understand light, we must go back to a time before it existed, or rather, a time before it could travel. We must go back to the very beginning, to the first moment. Imagine the universe in the first second after the Big Bang. It is not the black, starry void we see today. It is a blinding, searing fog. The temperature is billions of degrees. The density is infinite. Matter and energy are not yet separate things. They are a soup of subatomic particles, protons, electrons, and photons, smashed together in a space smaller than an atom. In this early universe, light is trapped. A photon, a particle of light, is born from the heat, but it cannot move. It travels a fraction of a millimeter before it crashes into an electron. It is absorbed, then spat back out, then absorbed again. It is a prisoner of the plasma. For 380,000 years, the universe is opaque. It is a glowing wall of fog. There are no stars, no galaxies, only this hot, thick hum of trapped energy. It is a cosmic dark age, ironically filled with blinding brilliance that has nowhere to go. But the universe is expanding, and as it expands, it cools. The violent energy of the particles begins to settle. The electrons, which have been buzzing wildly, slow down enough to be captured by the protons. They click into orbit. This moment is known as recombination. It is the most important sunrise in history. Suddenly, the fog clears. The electrons are locked away in atoms of neutral hydrogen. The path is open. The photons, released from their prison, stream outward in every direction. The universe becomes transparent. The light that was released in that moment is still traveling today. We call it the cosmic microwave background. It is the afterglow of the Big Bang, a faint whisper of radiation that fills every corner of space. When you tune an old television between channels, a small percentage of that static is this ancient light landing on your screen after a journey of 13.8 billion years. But that ancient light is cool and dim now. To see the light that warms our days, we must look closer to home. We must look at a star. We must look at our sun. Our sun is a factory of light. It is a sphere of gas 100 times wider than the Earth, held together by its own crushing gravity. In the center of this sphere, the conditions are hellish. The temperature is 15 million degrees. The pressure is 300 billion times greater than the atmosphere of Earth. Here, in the core, matter is stripped of its identity. Hydrogen atoms are crushed together so violently that they fuse. They turn into helium. And in that moment of fusion, a tiny amount of mass is lost. It is converted into pure energy, obeying Einstein's equation, E equals mc squared. That energy is born as a photon, a single particle of light. But this is not the gentle yellow light we see from the garden. This is a gamma ray. It is a high-energy scream of radiation, violent and destructive. If you were exposed to it, you would be vaporized instantly. This newborn photon begins its journey. Its destination is the surface of the Sun, and then the Earth. The distance from the center of the Sun to its surface is about 700,000 kilometers. At the speed of light, it should take 2 seconds to cross, but it does not take 2 seconds. It takes 100,000 years. This is the great struggle of the light. The core of the Sun is incredibly dense. It is 150 times denser than water. It is a crowded room packed with charged particles. The photon cannot move in a straight line. It travels a tiny fraction of a centimeter and, smack, it hits a proton. It is absorbed. The proton shudders with the energy and then spits the photon out again, but it spits it out in a random direction. Maybe forward, maybe backward, maybe sideways. The photon travels another tiny distance, smack, another collision, another random redirection. This is called the random walk, or the drunkard's walk. The photon is pinballing through the dense plasma, taking billions of steps just to move an inch. It is a labyrinth without walls. The photon might spend 1,000 years just circling the center, making no progress at all. It is trapped in a game of chance. As it fights its way outward, slowly migrating from the core to the radiative zone, it changes. Every collision steals a little bit of its energy. The violent gamma ray is stretched. It becomes an X-ray. It becomes an ultraviolet ray. It is aging. It is cooling down. By the time it reaches the upper layers of the Sun, the convection zone, the plasma is churning like boiling water. Giant bubbles of hot gas rise to the surface, carrying the light with them. The journey accelerates. Finally, after millennia of struggle, the photon reaches the photosphere. This is the visible surface of the Sun. The density drops. The crowd thins out. The path ahead is clear. In one last interaction, the atom releases the photon. It is no longer a gamma ray. It has been tamed. It is now a particle of visible white light. It is free. It launches into the vacuum of space, and now, for the first time in its long life, it can show its true nature. It accelerates instantly to the cosmic speed limit, 300,000 kilometers per second. It does not need to build up speed. Light is born moving at top speed. It cannot go slower. If it exists, it moves. It crosses the distance from the Sun to the Earth, 150 million kilometers, in 8 minutes and 20 seconds. It flies past Mercury, scorching the rocks. It flies past Venus, reflecting off the thick white clouds. It races through the silence of the void. Space is empty. There are no protons to hit, no friction. The light travels in a perfect straight line, a wave of electric and magnetic energy oscillating in harmony. It carries the news of the Sun. It carries the heat that will drive the wind and the weather. Then it hits the atmosphere of Earth. The journey changes again. The vacuum ends. The air begins. The atmosphere is a blanket of nitrogen and oxygen molecules. As the white light of the Sun hits these molecules, it scatters. The white light is made of all colors: red, orange, yellow, green, blue, indigo, violet. Each color has a different wavelength. Blue light moves in short, choppy waves. Red light moves in long, lazy waves. The short blue waves crash into the nitrogen molecules and scatter in every direction. They bounce around the sky, painting the dome blue. The longer red and yellow waves are able to dodge the molecules, passing through relatively straight. This is why the sky is blue and the Sun looks yellow. It is a trick of scattering. At sunset, the light has to travel through much more air to reach your eye. Most of the blue is scattered away completely, leaving only the deep reds and oranges to touch the clouds. But let us follow a single photon that makes it through the blue haze. It falls downward, through the clouds, through the leaves of a tree, and lands on a surface. Let us say it lands on the leaf of a fern in a forest. This moment is the foundation of all life on Earth. The photon strikes a molecule of chlorophyll within the leaf. The energy of the light knocks an electron loose. This captured energy is used to split a water molecule, releasing oxygen and creating sugar. This is photosynthesis. It is the process of turning light into food. Every apple you eat, every slice of bread, every piece of meat, it is all stored sunlight. The energy that moves your muscles right now is the same energy that was forged in the core of the sun 100,000 years ago, traveled across space, and was caught by a plant. We are light eaters. Or perhaps the photon does not hit a leaf. Perhaps it hits something else. Perhaps it hits your eye. You are standing in a garden. The photon passes through the clear window of your cornea. It swims through the fluid of your eye. It passes through the lens, which focuses it, and it strikes the retina at the back of your eye. The retina is a carpet of sensitive cells, rods and cones. Inside one of these cells, there's a protein called rhodopsin. When the photon hits the rhodopsin, the protein changes shape. It snaps. This microscopic movement triggers a chemical cascade. It generates an electrical impulse. The impulse travels down the optic nerve into the dark interior of your brain, to the visual cortex. Your brain receives the signal and says, light. It says, green. It constructs an image. The world you see, the colors, the shapes, the faces of your loved ones, is a reconstruction happening inside your head, built from the impacts of billions of photons. Vision is the sense of touching the universe from a distance. When you look at a star, your eye is physically touching a photon that has traveled for 1,000 years just to end its life on your retina. It is a form of intimacy with the cosmos. But light is tricky. It is not just a particle. It is also a wave. This is the great duality that puzzled scientists for centuries. Is it a grain of sand, or is it a ripple in the water? The answer, strangely, is yes. If you fire light through two tiny slits in a wall, it behaves like a wave. The ripples interfere with each other, creating a pattern of light and dark bands on the other side. But if you measure it with a detector, it arrives as discrete lumps, photons. It seems to know when it is being watched. Light behaves like a wave when it travels, and a particle when it lands. It is a shapeshifter, and it has a speed limit. Nothing in the universe can travel faster than light. This limit, 299,792,458 meters per second, is not just a number. It is the speed of causality. It is the speed at which cause leads to effect. Time threes. Because light takes time to travel, looking out into space is looking back in time. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. If the sun vanished right now, we would not know for 8 minutes. We would still see it shining in the sky. We would still feel its gravity. We would still be warm. When you look at the nearest star, Alpha Centauri, you are looking 4 years into the past. And when you look at the Andromeda Galaxy, a smudge of light in the night sky, you are seeing light that left its source 2.5 million years ago. You are looking at a time before humans existed. That light has been traveling through the void while ice ages came and went, while civilizations rose and fell, while you were born and grew up. It arrives only now. The night sky is a time machine. We are trapped in a bubble of the present, surrounded by layers of the past. The farther we look, the older the universe gets. Light is the ruler we use to measure the universe, but it is also a mystery that refuses to be fully solved. It has no mass, yet it has momentum. It can push a solar sail. It does not experience time. From the perspective of a photon, the journey from the star to your eye takes 0 time. It is instantaneous. Birth and death happen at the same moment. For light, there is no distance and there is no time. There is only connection. This strange, luminous entity is the foundation of our reality. It defines our days and our nights. It sets our biological clocks. It feeds us. It allows us to know the universe. In the next chapter, we will break light apart. We will take the white light of the sun and pass it through a prism. We will explore the spectrum. We will look at the colors we can see, and the vast, invisible oceans of light we cannot, the infrared, the ultraviolet, the radio waves. We will see that the visible world is only a tiny fraction of reality. For now, close your eyes. Imagine the darkness behind your lids. Even there in the dark, there's a faint shimmer. The visual neurons are never fully silent. You are a creature of light, made of atoms that interact with light, living on a planet bathed in light. The story of light is the story of everything you have ever seen. When we look at the world, we see a tapestry of color. The green of the forest, the blue of the ocean, the red of the rose. We assume that these colors belong to the objects themselves, that redness is a property of the rose in the same way that weight or texture is. But this is an illusion. The world outside our eyes is colorless. It is a place of silent, invisible radiation. To understand where color comes from, we must break light apart. We must do what Sir Isaac Newton did in 1666, in a darkened room in Woolsthorpe Manor. He bored a tiny hole in his window shutter, allowing a single, thin beam of white sunlight to enter the darkness. In the path of this beam, he placed a triangular piece of glass, a prism. What happened next changed our understanding of reality forever. The white light did not just pass through the glass, it was dismantled. It fanned out onto the opposite wall in a brilliant band of colors: red, orange, yellow, green, blue, indigo, violet. Newton called this the spectrum, from the Latin word for ghost or apparition. Before Newton, people believed that white light was pure and that colors were added to it by darkness or matter. But Newton proved that white light is not pure at all. It is a choir. It is a mixture of all the visible wavelengths singing together. The prism simply unraveled the harmony, allowing us to see the individual notes. But what is color? Physically, it is nothing more than a measurement of distance. Light travels in waves, ripples in the electromagnetic field. The distance between two peaks of a wave is its wavelength. Red light is long and lazy. Its waves are about 700 nanometers apart. It moves with a slow, rolling rhythm. Violet light is short and energetic. Its waves are bunched tight, only 400 nanometers apart. It vibrates with a frantic intensity. Green lies in the middle, a perfect balance. That is all color is, a ruler measuring the length of a wave. The universe contains no red or blue. It contains only wavelengths. The sensation of color is created entirely inside your head. It is a translation code used by the brain to distinguish between different energies of light. When you look at a red apple, the apple is not red. The skin of the apple contains pigments that absorb almost every wavelength of light, the blues, the greens, the yellows. But it rejects the long, red wavelengths. It bounces them away. The redness of the apple is precisely the part of the light that the apple doesn't want. We see the leftovers. This visible spectrum, the rainbow we can see, is incredibly narrow. It represents a tiny fraction of the light that actually exists. Imagine a piano, keyboard that stretches from the earth to the sun. The keys representing the visible colors would take up less than an inch of that keyboard. The rest of the keys are playing notes we cannot see. If we could widen the doors of perception, if we could tune our eyes to other frequencies, the world would transform into something alien and spectacular. Let us travel beyond the red edge of the rainbow. Just below red lies the infrared. Infra means below. We cannot see this light, but we can feel it. It is the warmth of the sun on your skin. It is the heat radiating from a fire. If you had infrared eyes, the night would not be dark. You would see the world glowing with its own internal heat. You would see the warm blood pumping through the veins of a sleeping animal. You would see the engine of a car cooling down hours after it was parked. You would see the heat escaping from the windows of houses, rising like smoke into the cool air. The world would look like a landscape of fire and ice. Snakes, like pit vipers, have evolved to sense this world. They have tiny pits on their faces that detect infrared radiation, allowing them to strike warm-blooded prey in absolute darkness. They hunt by the light of body heat. Further down the keyboard, the waves get longer and longer. We reach the microwaves. These are the waves that vibrate water molecules heating our food. And beyond them, the radio waves. These are the giants. Some radio waves are as long as a football field. Others are as long as a planet. These waves pass through us constantly. They carry the music of the radio, the data of the internet, the signals of our cell phones. We are walking through a blizzard of information, encoded in light that is too tired to see. Now let us go the other way. Let us travel past the violet edge. Just above violet lies the ultraviolet. Ultra means beyond. This light is energetic. It carries enough punch to damage living cells. It is the light that causes sunburn. We cannot see it, but many animals can. Bees see patterns on flowers that are invisible to us, bullseyes and landing strips painted in UV pigment, guiding them to the nectar. Birds see UV markings on each other's feathers, signals of health and mate quality. To a bird, a black feather might shine with a dazzling, secret color that we have no name for. Further up the scale, the waves get shorter and tighter. We reach the X-rays. These wavelengths are so small they can slip between the atoms of soft tissue, blocked only by the dense calcium of bone. They allow us to see the skeleton inside the living body. And finally, at the very top of the scale, we find the gamma rays. These are the screams of the universe. Created by exploding stars and colliding black holes, they are the most energetic form of light. A single gamma-ray photon carries more energy than 1 million visible photons. This entire range, From the giant radio waves to the microscopic gamma rays is the electromagnetic spectrum. It is all the same stuff. It is all light. The only difference is the length of the step it takes as it travels. But let us return to the narrow slice we call visible. Why do we see only this tiny band? Why did our eyes evolve to tune into this specific frequency? The answer lies in the ocean. Life began in the water. Radio waves cannot penetrate deep water. Ultraviolet light is blocked by water. But visible light, the blues and greens and yellows, passes through water with ease. Our ancient ancestors, the first fish and squids, developed eyes to see in the specific wavelengths that filtered down from the surface. We essentially have fish eyes, tuned to the light of a watery world we left hundreds of millions of years ago. We still carry the ocean in our retinas. But our perception of color is not just about physics. It is about biology. It depends on the machinery of the eye. The human retina contains millions of tiny cells called cones. Most people have 3 types of cones, one sensitive to red, one to green, and one to blue. We are trichromats. Every color you have ever seen is a mixture of these 3 signals. Your brain acts like a painter, mixing red, green, and blue paints to create the millions of hues of reality. Yellow is just red and green firing together. White is all 3 firing at once. But not everyone sees the same world. Most mammals, dogs, cats, cows, are dichromats. They have only 2 types of cones. They see the world in shades of blue and yellow. To a dog, a red ball on green grass looks like a muddy yellow ball on muddy yellow grass. They live in a simpler visual reality. On the other hand, birds and reptiles are often tetrachromats. They have 4 types of cones. They can see colors we cannot even imagine. A butterfly sees a world of vibrancy that would overwhelm the human mind. The mantis shrimp, the champion of the visual world, has 16 types of color receptors. It looks at a coral reef and sees a symphony of color so complex it defies description. This realization is humbling. It means that what we see is not the truth. It is just our truth. It is a user interface designed for the human primate. We are looking at the universe through a keyhole. But even within our limited range, light does extraordinary things. It interacts with the atmosphere to create the sky. Why is the sunset red? As the sun dips lower, its light travels through a thicker slice of the atmosphere. The blue light, which scatters easily, is filtered out completely. It is scattered away to the other side of the world, creating the blue sky for someone else's morning. What remains is the sturdy red light, the long wavelengths that can punch through the thick air, the dust, and the pollution. The sunset is the survivor light. It is the light that made it through the gauntlet. And then there is the green flash, a rare, momentary pulse of emerald light that can appear on the horizon just as the sun disappears. It is a mirage, a trick of refraction where the atmosphere acts like a prism, bending the green light just enough to let it peek over the curve of the Earth for a split second. Light also plays tricks with time. We see the stars twinkling. This is not the star changing. It is the turbulence of our own air. Pockets of warm and cold air act like lenses, bending the starlight back and forth. The star is steady. It is our atmosphere that is trembling. But perhaps the most beautiful interaction of light is the rainbow. It is the spectrum written in the sky. For a rainbow to form, you need rain in front of you and the sun behind you. Each raindrop acts like a tiny prism and a tiny mirror. Light enters the drop, bends, refracts, reflects off the back of the drop, and bends again as it leaves. Because different colors bend at different angles, they separate. Red comes out at 42 degrees, violet at 40 degrees. Millions of drops working in concert paint a perfect arc of color. But here's the secret of the rainbow. It is not an object. It does not exist in a specific place. You can never walk under the arch. If you move, the rainbow moves with you. It is an optical illusion created specifically for your eye. Each person sees a slightly different rainbow, created by a different set of raindrops. It is a private show, performed by the laws of physics just for you. The interaction of light and matter goes deeper than simple reflection. It creates the phenomenon of fluorescence. Some materials absorb invisible ultraviolet light and re-emit it as visible light. Scorpions glow a ghostly blue under UV light. Tonic water glows blue because of the quinine in it. Even our own teeth glow faintly. It is a way of converting high-energy danger into low-energy beauty. Light is also a carrier of information. Fiber optic cables, the backbone of the internet, carry pulses of light through strands of glass. Your voice, your emails, this very story, they are all turned into flashes of laser light, bouncing down a glass tunnel at the speed of the universe. We have learned to domesticate the photon. As we look at the colors around us, the warm wood of the floor, the cool white of the sheets, we are seeing the signature of electrons dancing. When light hits an object, the electrons in the atoms absorb energy. They jump to a higher orbit. Then they fall back down, releasing that energy as a new photon of color. The world is constantly absorbing and re-emitting light. It is a conversation between matter and energy that never stops. In the next chapter, we will look at the source of it all. We have looked at the light. Now we will look at the lamp. We will travel to the sun. We will explore the violent magnetic storms that rage on its surface. We will look at the solar wind that buffets the earth. We will see how the sun breathes, pulsing with an 11-year cycle that dictates the weather of the entire solar system. For now, imagine the spectrum. Imagine the colors flowing around you like a river, visible and invisible, warm and cool. You are bathed in a sea of frequencies. The darkness of the room is not empty. It is full of infrared heat from your body. It is full of radio waves carrying songs you cannot hear. It is full of the quiet potential of light. Rest in the colorful dark. We have taken the light apart. We have seen the hidden rainbows and the invisible colors that paint the world. But light does not arise from nothing. It requires a source. It requires a fire. And so, we must travel to the heart of our solar system. We must turn our gaze towards the lamp that lights our days. We travel to the sun. From the Earth, it looks like a perfect yellow coin. It sits in the sky, steady and unchanging, rising and setting with a clockwork rhythm that has comforted life for billions of years. We call it Sul. We worship it as a god of order. But if we fly closer, if we strip away the blinding glare and look at the surface, we find that our perception of calmness is a lie. The sun is not a solid object. It is a roaring, chaotic ocean of fire. It is a ball of plasma, a state of matter where atoms are ripped apart, electrons separated from nuclei, creating an electrically charged gas that behaves like a fluid. and this fluid is boiling. The surface of the Sun, the photosphere, is not smooth. It is textured like the skin of an orange. These textures are called granules. Each granule is a bubble of hot gas rising from the deep interior, releasing its heat into space, and then sinking back down as it cools. They look small from a distance, mere speckles, but each one of these bubbles is the size of Texas. The entire surface of the star is covered in millions of them, a shifting mosaic of convection cells that turn over every 20 minutes. The face of the Sun is constantly replacing itself. It is a landscape of geysers, wider than continents, erupting continuously for 4 billion years. If we could hear the sound of this violence, it would be deafening. The Sun rings like a bell. The constant churning of the gas creates sound waves that travel through the interior, bouncing off the core and returning to the surface. These sound waves cause the entire star to vibrate, to pulse in and out. Scientists call this helioseismology. By listening to the music of the Sun, by measuring the frequency of these vibrations, we can map the inside of the star just as earthquakes allow us to map the inside of the Earth. The Sun is singing a low, resonant song into the void, a frequency far too deep for human ears, but powerful enough to shake the solar system. But the heat and the sound are only the beginning. The true ruler of the Sun is magnetism. Because the Sun is made of plasma, charged particles, its movement creates magnetic fields. And because the Sun is not solid, it does not spin evenly. The equator of the Sun spins faster than the poles. A point on the equator takes about 25 days to complete a rotation, while a point near the pole takes 35 days. This differential rotation is the engine of solar violence. Imagine the magnetic field lines as rubber bands running from north to south. As the equator spins faster, it drags these rubber bands with it. They get stretched. They get wrapped around the belly of the Sun. They twist and tangle, getting tighter and tighter with every rotation. Eventually, the tension becomes too great. The magnetic lines snap. They burst through the surface of the Sun, looping out into space and then diving back in. Where these magnetic loops pierce the surface, they act like dams. They hold back the rising hot gas from below. The gas in these areas cools down. It creates a dark patch on the blinding surface. We call these sunspots. To our eyes, sunspots look black, but this is an illusion of contrast. They are only dark because they are sitting next to the brilliance of the photosphere. If you could scoop out a sunspot and place it in the night sky, it would shine brighter than the full moon. It would glow an angry red. These spots are immense. Some are large enough to swallow the Earth 10 times over. They are islands of magnetism floating in the sea of plasma. And they are not static. They migrate. They change shape. They are the visible symptoms of the magnetic war raging below. Above the sunspots, the magnetic loops stretch high into the Sun's atmosphere, the corona. The corona is a halo of ghostly white plasma that extends millions of kilometers into space. It is one of the great mysteries of astrophysics. The surface of the Sun is 6,000 degrees, but the corona is millions of degrees. It is hotter than the fire that feeds it. It is as if you walked away from a campfire, and the air got hotter the further you went. We believe this heat comes from magnetic reconnection, the snapping and reforming of the magnetic loops, releasing explosive energy like a whip cracking. When these magnetic loops become too twisted, they can cross. Like a short circuit, they reconnect violently. This releases a blast of radiation known as a solar flare. A flare is a flash of light that screams across the entire electromagnetic spectrum, from radio waves to gamma rays. In a matter of minutes, a single flare can release more energy than millions of volcanic eruptions. It is a tsunami of light. But sometimes, the sun throws more than just light. Sometimes, it throws matter. This is a coronal mass ejection, or CME. 1 billion tons of plasma, protons, electrons, heavy ions, is hurled into space. It is a cannonball of fire. It travels at millions of kilometers per hour, tearing through the vacuum. If the Earth happens to be in the path of this cannonball, the consequences are profound. But the sun does not just emit energy in bursts. It also flows. There's a constant stream of particles leaving the star in all directions, all the time. It is called the solar wind. The sun is evaporating. Every second it loses 1 million tons of mass to this wind. It is blowing a bubble around itself. This wind is not like the wind on Earth. It is a stream of radiation. It rushes past Mercury, past Venus, and washes over the Earth. This brings us to the interaction between the lamp and the world it lights. The Earth is swimming in the atmosphere of the sun. We are not separate from it. If the Earth were a dead rock, the solar wind would strip away our atmosphere. It would scour the surface clean, leaving a barren desert like Mars. But the Earth is alive. It has a shield. Deep in the center of our planet, a core of molten iron spins. It generates a magnetic field that reaches far out into space. This is the magnetosphere. It is an invisible force field that surrounds our world. When the solar wind hits this shield, it is deflected. It flows around the Earth like water flowing around a stone in a stream. The violence of the sun is pushed aside, leaving a calm wake in which our atmosphere can cling to the surface. But the shield is not perfect. Near the poles, the magnetic field lines curve inward, funneling down toward the ground. Some of the solar particles manage to ride these lines. They spiral down into the upper atmosphere. When these high-energy particles from the sun crash into the atoms of oxygen and nitrogen in our air, they transfer their energy. The atoms become excited. They light up. This is the aurora, the northern and southern lights. It is the visible sign of the connection between the star and the planet. It is the solar wind painting the sky. The colors tell us which atoms are being hit. Green, the most common color, comes from oxygen atoms low in the atmosphere. Red comes from oxygen high up, near the edge of space. Blue and purple come from nitrogen. To stand under an aurora is to watch the mechanics of the cosmos with the naked eye. Curtains of light shimmer and fold, dancing to the rhythm of a magnetic storm 93 million miles away. It is a silent display, but it speaks of immense power. It reminds us that we are protected by a fragile, invisible cage of magnetism. The sun itself has seasons. It breathes. It has a heartbeat that spans 11 years. This is the solar cycle. At solar minimum, the sun is quiet. The same face is blank, free of sunspots. The magnetic field is organized. The solar wind is steady. But as the years pass, the differential rotation winds up the magnetic field. The tension builds. Sunspots appear. Flares erupt. The sun becomes angry. This is solar maximum. The star is covered in blemishes, spitting fire and storms into the system. Then, at the peak of the chaos, the magnetic poles of the sun flip. North becomes south. South becomes north. The tension releases. The knots untie. The sun calms down, returning to minimum, and the cycle begins again. We have been tracking these cycles for centuries. We can see them in the growth rings of ancient trees, which record the levels of radiation from centuries past. We can see them in the records of medieval astronomers who wondered why the sun had spots. Sometimes, the sun enters a deep sleep. In the 17th century, the sunspots vanished for 70 years. This was the Maunder minimum. It coincided with the Little Ice Age on Earth. The Thames in London froze solid. The winters were brutal. It showed us that even a tiny variation in the light of the lamp can change the destiny of civilizations. But the influence of the sun extends far beyond Earth. The solar wind does not stop at us. It continues outward, past Mars, past the gas giants Jupiter and Saturn, past the icy realm of Pluto. It blows a vast bubble in the interstellar medium. This bubble is called the heliosphere. It is the domain of the sun. Inside this bubble, the environment is dominated by the solar wind. Outside, it is the domain of the other stars. The heliosphere acts as a shield for the entire solar system. It pushes back against the high-energy cosmic rays coming from the galaxy, the shrapnel of exploding stars deep in the Milky Way. Without the heliosphere, the radiation in our solar system would be far more intense. The sun protects its children. We have sent emissaries to the edge of this bubble. The Voyager probes, launched in the 1970s, have traveled for decades. They have crossed the termination shock, where the solar wind slows down and piles up against the interstellar gas. They have entered the heliopause, the final boundary. There, the wind from the sun finally dies. It merges with the cold, thin wind of the galaxy. Beyond that line, the sun is just another bright star in the sky. It is a lonely, majestic boundary, a wall of wind holding back the dark. But the sun is not eternal. Like any fire, it consumes fuel. It is halfway through its life. It has been burning for 4.5 billion years, and it has about 5 billion years left. Pitch 1%. It is a main sequence star, fusing hydrogen into helium. It is in its prime. It is stable. It is the perfect host for life. But slowly, imperceptibly, it is getting brighter. As the helium builds up in the core, the pressure increases. The furnace burns hotter. In 1 billion years, the sun will be 10% brighter than it is today. That extra heat will be enough to boil the oceans of Earth. The story of life on this planet has a time limit, dictated by the metabolism of our star. Eventually, the hydrogen will run out. The core will collapse. The outer layers will swell. The sun will become a red giant. It will grow large enough to swallow Mercury and Venus. It might even swallow Earth. The lamp will become an inferno. And then it will shed its skin. The outer layers will drift away, forming a beautiful planetary nebula, a flower of glowing gas. The core will remain behind as a white dwarf, a tiny, dense crystal of carbon and oxygen, no bigger than the Earth, glowing with stored heat. It will no longer generate energy. It will simply cool down, slowly fading over trillions of years until it becomes a black dwarf, a cold, dark cinder floating in the void. That is the destiny of the light, but that is a story for the distant future. For now, the sun is constant. It rises every morning, chasing away the shadows. It feeds the plants. It drives the wind. It warms our skin. It is the anchor of our existence. Everything we are, everything we eat, every breath we take is powered by the photons that struggled for 100,000 years to escape the core and then flew for 8 minutes to touch us. We are solar-powered beings. We are condensed sunlight. In the next chapter, we will leave the sun behind. We will follow the light as it interacts with the one thing that can trap it, hold it, and use it. We will travel into the green world. We will explore photosynthesis. We will see how a leaf captures a photon and turns it into sugar. We will look at the machinery of the chloroplast, the true foundation of the food chain. We will see how light becomes life. For now, imagine the sun hanging in the black sky, a churning, roaring magnetic sphere of generosity, pouring itself out into the cold, asking for nothing in return. Feel the warmth of it in your memory. Let the golden light fill your mind. You are safe in the orbit of a kind star. We have stood in the roaring furnace of the sun, and we have watched the solar wind paint the sky with auroras. But now, we must follow the light to its most important destination. We travel across the vacuum of space, through the blue haze of the atmosphere, and land softly in a quiet place. We land in a forest. It is cool here. The air smells of pine needles, damp earth, and decaying wood. It seems silent, static, peaceful. But this peace is an illusion. If we could tune our senses to the molecular level, we would hear a hum of industry so loud it would rival the noise of any city. We are standing in the middle of the greatest factory on Earth. Every leaf, every blade of grass, every algal bloom on the surface of the pond is a machine. They are the engines that drive the biosphere, and their fuel is the photon. To understand how light becomes life, we must shrink. We must pass through the waxy skin of a leaf, the cuticle, and enter the interior. Here, we find a labyrinth of air pockets and water channels. And lining the walls of these channels are the cells. Inside these cells float small, green, disc-shaped organs called chloroplasts. They move. If the light is too weak, they drift toward the surface of the cell to catch every ray. If the light is too strong, they retreat to the sides to avoid being burned. They are intelligent, light-seeking entities. There is a reason they look like independent creatures. Billions of years ago, they were. The chloroplast was once a free-living bacteria, a cyanobacterium swimming in the primordial ocean. It was eaten by a larger cell, but instead of being digested, it struck a deal. It offered to make food in exchange for shelter. This ancient pact, endosymbiosis, is the reason plants exist. Every tree is a colony of ancient bacteria living inside modern architecture. Let us dive inside one of these chloroplasts. It is filled with stacks of membranes called thylakoids. They look like stacks of green pancakes. Embedded in these membranes is a molecule that changed the destiny of our planet: chlorophyll. Chlorophyll is a pigment. It is a molecule shaped like a tennis racket, with a head of magnesium designed to catch energy. It is the reason the world is green. But why green? The sun pours down white light, a mixture of all colors. Chlorophyll is hungry for the high-energy blue light and the warm red light. It absorbs them greedily. But it has no use for the green light in the middle of the spectrum. So, it bounces it away. It reflects it into our eyes. The green of the forest is the light the plants rejected. We see the waste product of their feast. Now, the moment of magic. A single photon of red light, having traveled 93 million miles from the sun, strikes a molecule of chlorophyll. It hits the magnesium atom in the center. The energy of the photon is transferred to an electron. The electron becomes excited. It jumps to a higher energy level. It vibrates with the power of the sun. In most materials, this energy would just turn into heat. The brick wall gets warm in the sun. But the plant does not want heat. It wants power. Before the electron can fall back down and lose its energy, the chloroplast grabs it. It steals the excited electron. This is the first step of photosynthesis. The plant has successfully captured a piece of the sun, but now the chlorophyll has a problem. It has lost an electron. It has a hole in its structure. It needs to replace it, and quickly, or the system will break down. Where can it find a spare electron? It turns to the most abundant substance around: water. Water, H2O, is a very stable molecule. Hydrogen holds on to oxygen with a tight, jealous grip. To rip them apart requires immense energy. But the chlorophyll, charged by the sun, becomes the strongest oxidizing agent in biology. It is an electron thief. It grabs a water molecule and tears it apart. It rips the electrons off the hydrogen atoms to plug its own hole. This is violence on a molecular scale. It is called photolysis, splitting by light. The hydrogen atoms are left as naked protons. But the oxygen atom? The plant has no immediate use for it. It is a waste product. So, the plant pairs it with another oxygen atom and releases it. The gas drifts out of the chloroplast, out of the cell, and out of the leaf through tiny pores called stomata. It drifts into the atmosphere. This waste product is oxygen. The air we breathe, the gas that keeps our blood red and our fires burning, is the exhaust fumes of this water-splitting machinery. 2.5 billion years ago, when this machinery first evolved, it caused a catastrophe, the Great Oxidation Event. Oxygen was toxic to the ancient life forms of Earth. The plants poisoned the atmosphere with their breath, wiping out nearly everything else. But that poison paved the way for us. We are the children of the oxygen catastrophe. Meanwhile, back in the leaf, the plant has its electrons. It uses them to run a tiny electrical current across the membrane. This current pumps protons into a reservoir, creating a battery. This battery powers a tiny spinning motor called ATP synthase. It is a literal rotor engine, spinning thousands of times a minute, churning out chemical fuel called ATP. So now the plant has energy, ATP, and reducing power, NADPH, but it still hasn't made any food. It has only charged its batteries. The next step is to build the structure. It needs carbon. The plant opens its stomata again. It inhales carbon dioxide from the air. This gas is the heavy, stable ash of combustion. It is what is left over when things burn. The plant takes this burnt ash and brings it into the Calvin cycle. Here, an enzyme called rubisco, the most abundant protein on Earth, grabs the CO2 and welds it onto a carbon chain. It uses the energy from the sun-charged batteries to force the atoms together. It takes 6 turns of the cycle to make 1 molecule of sugar, glucose. This sugar is a miracle. It is a trapped packet of solar energy. It is crystallized light. The energy that was fusion in the sun is now a chemical bond in a leaf. The plant uses this sugar to build itself. It links the sugar molecules together to form long chains of cellulose. This is wood. This is fiber. This is the trunk of the oak and the stem of the wheat. Think about what this means. When you look at a giant redwood tree, towering 300 feet into the air, weighing tons, where did all that mass come from? It did not come from the soil. The soil provides only tiny amounts of minerals. The mass of the tree came from the air. It is built out of thin air, spun into solid wood by the power of light. A tree is a solidified breath. It is a cathedral built of carbon dioxide. This process is the foundation of the entire food chain. The plant eats the light. The herbivore eats the plant to get the sugar. The carnivore eats the herbivore. When you eat an apple, you are breaking the chemical bonds that the apple tree built. You are releasing the stored energy of the sun to power your muscles. When you run, you are running on sunlight. When you think, your brain is burning ancient photons. Even the dead serve the light. Consider the Carboniferous period 300 million years ago. Vast swamp forests covered the earth. When these trees died, they fell into the muck and did not rot. They were buried, compressed, and cooked by the heat of the earth. They became coal. They became oil. When we burn coal today to generate electricity, we are releasing the sunlight that fell on the earth 300 million years ago. We are unlocking the battery that was charged in the deep past. The light in your lamp is the ghost of a prehistoric sunbeam. The entire biosphere is a flow of this energy. It streams from the sun, flows through the plants, cascades through the animals, and eventually dissipates as heat returning to space. Life is a way of slowing down the light, holding on to it for a moment and dancing with it before letting it go. But not all light comes from the sun. In the deepest parts of the ocean, where the sun never shines, there is still light, but it is not from above. It is from within. This is bioluminescence. Down in the abyss, creatures have learned to make their own light. They carry chemicals, luciferin and luciferase. When they mix them with oxygen, a cold fire is born. Anglerfish dangle glowing lures to attract prey in the dark. Squid spray clouds of glowing ink to confuse predators. Tiny plankton flash when disturbed, creating sparkling trails in the water. On land, we see it in fireflies, a meadow in summer filled with blinking yellow lights. This is not the passive reflection of the sun. This is biological agency. It is life deciding to shine. It is a chemical reaction that is nearly 100% efficient. A light bulb wastes 90% of its energy as heat. A firefly wastes almost nothing. It is pure light. Why do they do it? To find a mate, to warn a predator, to lure a meal. Light is the universal language of attention. Even in the dark, life yearns for the visual. But let us return to the surface. Let us return to the green leaf. There is a subtle breathing that happens across the entire planet. NASA satellites can watch the Earth breathe. In the northern summer, the vast forests of Siberia, Canada, and Europe leaf out. They inhale gigatons of carbon dioxide from the atmosphere to build their bodies. The global CO2 levels drop. In the northern winter, the leaves fall and rot. They exhale the carbon back into the air. The CO2 levels rise. The Earth has a heartbeat, driven by the tilt of its axis and the hunger of its plants. We live inside this rhythm, and the plants are not just passive collectors. They are hunting the light. Watch a time lapse of a forest floor. The seedlings are in a desperate, slow-motion war. They stretch, twist, and race each other for the patch of sunlight that breaks through the canopy. They murder each other with shade. It is a silent green violence, but they also cooperate. Under the soil, the roots are connected by a fungal network, the Wood Wide Web. Through this network, a large tree in the sun can send sugar to a small sapling in the shade. The light is shared. The forest acts as a community to maximize its harvest of the sun. This interaction, light hitting matter, is the engine of everything. But there is one interaction that is even more intimate than photosynthesis, one that does not build sugar, but builds reality itself. It is the interaction between light and the eye. For billions of years, life was blind. It felt the heat, it sensed the chemicals, but it could not see. Then, a simple cell developed a protein that reacted to light. It became a spot, then a cup, then a lens. The invention of the eye triggered the Cambrian explosion. Suddenly, there were predators who could hunt and prey who could hide. The arms race of visibility began. Light became information. In the next chapter, we will follow the light as it enters the most complex biological structure known to science. We will travel into the human eye. We will see how the lens focuses the world upside down. We will visit the retina, a carpet of nerves that drinks the photons. We will understand how the brain takes two streams of electrical gibberish and weaves them into the 3D cinema of consciousness. We will explore why we see in color, why the dark frightens us, and how we have learned to extend our vision beyond the limits of our biology with telescopes and microscopes. For now, imagine the forest around you. The sun has set. The photosynthesis has stopped. The factories are closing for the night. The trees are resting, holding their breath. The stored sunlight in the wood keeps the forest warm. The energy is waiting. You are part of this cycle. You are a being of light, resting in the dark. We have followed the light from the core of the star to the leaf of the tree. We have seen it build the biomass of the planet. But light has another function, one that is perhaps even more profound than providing energy. It provides information. It carries the image of the world. For the first 3 billion years of life on Earth, the planet was a world of the blind. Life was single-celled, floating in the dark oceans. These creatures could taste the water. They could feel the heat. They could sense the vibration of a neighbor, but they could not see. The concept of over there did not exist. There was only here. Then, a random mutation occurred. A single cell developed a patch of protein that was sensitive to light. It was not an eye. It was just a spot, a freckle of pigment, but it gave that cell a superpower. It could tell the difference between light and dark. It could orient itself. It knew which way was up, toward the sun and the food. This was the beginning of the arms race of vision. Over millions of years, the spot deepened into a cup. The cup allowed the creature to tell the direction of the light. Then, the cup closed over to form a pinhole, creating a sharp image. Finally, a lens evolved to focus the light. Suddenly, the lights turned on. This moment is known as the Cambrian explosion. About 540 million years ago, the diversity of life exploded. Why? Because animals could see each other. Predators could spot prey from a distance. Prey could see the shadow of the hunter. Camouflage evolved. Armor evolved. Speed evolved. The invention of the eye forced life to become complex. We are the children of that revolution. To understand the miracle of sight, let us follow a stream of photons as they enter the most sophisticated optical instrument in the known universe, the human eye. The eye is a sphere, about 24 millimeters across, filled with fluid. It is kept under pressure to maintain its shape. It is a biological camera, but one that repairs itself and focuses instantly. The light first hits the cornea. This is the transparent front window. It is a masterpiece of biological engineering. Most tissues in the body are opaque because they are full of blood vessels, but the cornea has no blood vessels. It must remain perfectly clear. It gets its oxygen directly from the air. It is the only part of your body that breathes from the outside. The cornea bends the light, performing the first stage of focusing. Then, the light travels through the pupil, the black hole in the center of the iris. The iris is a muscle, a colored ring that expands and contracts to control the amount of light entering the eye. It is the aperture. In bright sunlight, the iris constricts, turning the pupil into a pinprick to protect the delicate interior. In darkness, it dilates, opening wide to catch every stray photon. This adjustment happens automatically, driven by the oldest parts of the brain. Past the pupil, the light hits the lens. This is a crystalline structure, flexible and clear. It is surrounded by a ring of muscles. When you look at something close, the muscles squeeze the lens, making it fat and round. When you look at the horizon, the muscles relax, pulling the lens flat. This is accommodation. It allows you to shift focus from a book in your hand to a star in the sky in a fraction of a second. As we age, the lens hardens. It loses its flexibility. This is why, after the age of 40, many people need reading glasses. The machinery of focus begins to stiffen. After passing through the lens, the light travels through the vitreous humor, the clear jelly that fills the bulk of the eyeball. It flies through this inner ocean untouched until it crashes into the back wall, the retina. The retina is not just a screen, it is a carpet of nerves. It is actually a piece of the brain that has migrated out of the skull to sit in the eye. It is lined with 130 million photoreceptor cells. These are the rods and the cones. The cones are the artists. They are concentrated in the very center of the retina, the fovea. They detect color and fine detail. They need bright light to work. When you read or look at a painting, you are using your cones. The rods are the night watchmen. They are located on the periphery of the retina. They are completely colorblind, seeing only in black and white, but they are incredibly sensitive. A rod can detect a single photon. They are responsible for our night vision and our motion detection. This is why, at night, you can see a faint star better if you look slightly to the side of it. You are letting the light fall on the sensitive rods rather than the insensitive cones. When a photon strikes one of these cells, a chemical reaction occurs. A molecule called rhodopsin twists shape. This snaps a chemical switch, generating a tiny electrical impulse. The energy of the light has been converted into the language of the nervous system. Here is a strange fact. The image that lands on your retina is upside down. The lens inverts the world. The ceiling is on the floor. The sky is at your feet. But you do not see the world upside down. Why? Because you do not see with your eyes. You see with your brain. The electrical signals travel down the optic nerve. This is a thick cable of 1 million nerve fibers exiting the back of the eye. Where it leaves, there are no rods or cones. This creates a blind spot in your vision, but you never notice it. Your brain fills in the gap. It guesses what should be there based on the surrounding pattern and paints over the hole. The signals travel into the darkness of the skull. They reach the visual cortex at the back of the brain. Here, the raw data is disassembled. One part of the brain analyzes shape, another analyzes color, another analyzes motion, another analyzes depth. The image is shattered into millions of fragments of information. Then, in a miracle of computation that we still do not fully understand, the brain reassembles it. It flips the image right side up. It adds depth. It stabilizes the image so that the world doesn't jump around every time you move your eyes. It constructs a seamless, three-dimensional hallucination of reality. What you are seeing right now is not the world itself. It is a model of the world, built by your brain, updated in real time by the light entering your eyes. This explains optical illusions. An illusion is not a failure of the eye. It is a hack of the brain's software. It occurs when the brain's assumptions about light and shadow are proven wrong, but our vision is limited. We only see the visible spectrum, the rainbow. We are blind to the infrared heat of a body or the ultraviolet patterns on a flower. We are trapped in a narrow slice of reality. However, humans are not content with their biological limits. We are tool builders. We wanted to see more. And so, we learned to manipulate light with glass. In the 17th century, a Dutch draper named Antony van Leeuwenhoek learned to grind tiny spherical lenses. He placed them in a metal plate and looked at a drop of pond water. He was the first human to see the animalcules. He saw a universe of microscopic life, bacteria, protozoa, swimming and fighting in a drop of water. He opened the door to the microcosm. He showed us that life extends downward into the invisible. At the same time, in Italy, Galileo Galilei pointed a tube with two lenses toward the sky. He did not invent the telescope, but he was the first to use it for astronomy. He saw mountains on the moon. He saw the phases of Venus. He saw 4 moons circling Jupiter. He realized that the Earth was not the center of the universe. He opened the door to the macrocosm. These two inventions, the microscope and the telescope, are extensions of the human eye. They allowed us to break the barrier of scale. We could see the cells that make us and the stars that made the atoms. Today, our eyes have grown giant. The Hubble Space Telescope and the James Webb Space Telescope are eyes floating in the vacuum. They can see light that has traveled for 13 billion years. They can see in infrared, peering through dust clouds to see stars being born. We have built machines that see in X-rays, gamma rays, and radio waves. We have mapped the entire electromagnetic spectrum. We have turned the invisible into the visible. But the most profound aspect of vision is not the physics, it is the psychology. Light dictates our moods. We are phototropic creatures. When the sun goes down, our bodies release melatonin to make us sleep. When the sun rises, the blue light wakes us up. We suffer in the dark winter months, seasonal affective disorder, because our brains are starved of photons. We fear the dark. This is an evolutionary instinct. For millions of years, the predators owned the night. To be in the dark was to be vulnerable. Light meant safety. This is why we gather around fires. This is why we light our cities. We are pushing back the ancient fear with artificial suns. Vision is also the primary way we connect with each other. The eyes are the window to the soul. We read emotions in the tiny micro-movements of the muscles around the eyes. We judge trust by gaze. We fall in love through eye contact. When you look into someone's eyes, you are looking into the only part of their brain that is visible from the outside. You are seeing the light that has bounced off them, entered you, and is now being reconstructed in your mind. As the sun sets in the forest where we landed in the last chapter, the light changes. The rods in your eyes take over from the cones. The world loses its color and becomes a landscape of silver and gray. The Purkinje shift occurs. Red flowers look black, but blue flowers look bright gray. The resolution drops. The world becomes softer, vaguer. The sharp edges of the day dissolve into the mystery of the night. In the next and final chapter, we will look at the future of light. We will see how we have mastered the photon. We will look at the laser, coherent light that can cut steel or heal an eye. We will look at fiber optics, the rivers of glass that carry the internet. And we will look at the ultimate destiny of light in the universe, the heat death, the final fade to black. We will close the story by returning to the darkness from which we came, but carrying the knowledge of the light with us. For now, let your own eyes rest. You have used them all day to process millions of gigabytes of visual data. Close the shutters. Let the visual cortex spin down. Behind your eyelids, the show is over. The screen is dark. The camera is off. Rest in the comfort of your own internal shadow. We have watched the sun rise over the primordial earth. We have seen the rainbow hidden in the prism. We have traveled into the green machinery of the leaf and the delicate camera of the eye. But the story of light is not just about what nature has given us. It is about what we have done with it. For thousands of years, humans were passive receivers of light. We warmed ourselves by the fire. We read by the candle. We walked by the moon. We could create light, but we could not control it. It was always wild. It scattered in every direction, messy and chaotic. But in the 20th century, we learned to tame the photon. We learned to make it march in step. We created a form of light that had never existed in the history of the universe, not in the heart of any star, not in the explosion of any supernova. We created the laser. To understand the laser, we must look at how normal light behaves. Think of a light bulb. It sends out photons in a chaotic jumble. They have different colors, wavelengths. They move in different directions. They are incoherent. It is like a crowd of people in a stadium, all shouting different words at different times. It is noise. A laser is different. It is a choir. In a laser, every photon has exactly the same wavelength, the same pure color. And, more importantly, they are coherent. The crests and troughs of their waves line up perfectly. They move in unison, locked in phase. This was a theoretical dream long before it was a reality. Albert Einstein predicted the physics in 1917. He called it stimulated emission. He realized that if an excited atom, an atom holding extra energy, is hit by a photon of the right color, it doesn't just absorb it, it clones it. The atom releases its stored energy as a second photon. This new photon is identical to the first. It moves in the same direction with the same phase. 1 becomes 2, 2 become 4. It is a cascade of light. an avalanche of photons. To build a laser, you need a mirror. You trap these excited atoms between two mirrors. As the light bounces back and forth, passing through the atoms again and again, the avalanche grows. It becomes intense. It becomes concentrated. Finally, it bursts through one of the mirrors, which is partially transparent. A beam of pure, coherent light shoots out. It does not spread out like the light from a flashlight. It stays tight and focused. You can shine a laser at the moon, and the spot on the lunar surface will be only a few kilometers wide. We have used this tamed light to change the world. We use it to cut steel with the heat of a star. We use it to reshape the cornea of the eye, restoring sight. We use it to scan the barcodes of our groceries. We use it to measure the distance to the moon to within a few millimeters. But perhaps the most profound use of this tamed light is communication. We have poured the light into glass. This is the technology of fiber optics. It is the nervous system of the modern world. Under the streets of your city and across the floor of the dark ocean lie cables filled with strands of glass thinner than a human hair. This glass is purer than any window. If you had a window made of this glass that was kilometers thick, it would be as clear as air. Inside these strands, we fire pulses of laser light. The physics that keeps the light inside is called total internal reflection. When light hits the glass wall at a shallow angle, it doesn't pass through. It bounces back. It ricochets down the tube, traveling for miles without escaping. It is light trapped in a cage of its own reflection. These pulses, flash, darkness, flash, carry our voices, our videos, our knowledge. The entire internet is essentially a Morse code of laser light flickering through glass at the bottom of the sea. When you speak to someone on the other side of the world, your voice is turned into electricity, then into light, then back into electricity, and then into sound. You are speaking with photons. We have turned light into a carrier of meaning. But even with our mastery, light remains the master. It sets the rules. The most fundamental rule of all is the speed limit. The speed of light, denoted by the letter cease, is exactly 299,792,458 meters per second. This is not just how fast light goes, it is how fast reality goes. It is the speed of causality. Nothing with mass can reach this speed. As you accelerate an object, it gets heavier. To reach the speed of light, you would need infinite energy, and you would become infinitely heavy. It is an impassable wall. Only light, which has no mass, can travel at sank. And because it travels at sank, light experiences no time. This is one of the strangest truths of relativity. If you could ride a photon, the clocks would stop. From the perspective of a photon leaving a distant star, the journey across the galaxy, which takes 1,000,000 years from our perspective, happens instantly. To the light, emission and absorption are the same event. It is born in the star and dies in your eye in the same moment. For light, the universe is timeless. It connects everything instantly. We are the ones who wait. We are the ones trapped in time. This speed limit also means that the night sky is a history book. We can never see the universe as it is now. We can only see it as it was. When we look at the most distant galaxies captured by the James Webb Space Telescope, we are looking back 13 billion years. We are seeing the toddler pictures of the cosmos. We are seeing the light from the first generation of stars, the population 3 stars, which were massive, pure, and violent. But there is a limit to how far back we can see. We cannot see past the recombination event, that wall of fog we visited in Chapter 1. That is the horizon of time. And there is something happening to that ancient light. It is changing color. The universe is expanding. Space itself is stretching, growing larger every second. And as space stretches, it stretches the light waves traveling through it. Imagine drawing a wave on a rubber band, then pulling the rubber band. The wave gets longer. This is happening to the light from distant galaxies. A photon might start its journey as energetic blue light, but after traveling for billions of years through expanding space, its wavelength is stretched. It becomes red. This is redshift. If it travels long enough, it is stretched beyond red into the infrared, and then into microwaves, and finally into radio waves. The cosmic microwave background, that afterglow of the Big Bang, was once visible, blinding white light. But over 13 billion years of expansion, it has been stretched into cold, invisible microwaves. The universe has cooled down. The light has grown tired. This expansion tells us about the destiny of light. It tells us where the story ends. Astronomers have discovered that the expansion of the universe is accelerating. A mysterious force called dark energy is pushing the galaxies apart faster and faster. This means that in the distant future, the other galaxies will be pushed away from us so fast that their light can never reach us. They will disappear beyond the cosmic horizon. Future civilizations, billions of years from now, might look up and see a dark sky. They will see only the stars of their own galaxy. The rest of the universe will have vanished into the dark, red-shifted into oblivion. They might believe they are alone in the cosmos. And eventually, even the stars will die. We are living in the stelliferous era, the age of stars. But it is temporary. Stars run on fuel, and fuel is finite. One by one, the lights will go out. The massive blue stars die first, then the yellow suns like ours. The red dwarfs will burn for trillions of years, glowing dimly like embers in a dying fire. But they too will eventually fade. The universe will enter the degenerate era, filled with the corpses of stars, white dwarfs, neutron stars, and black holes. But even white dwarfs cool down. They will become black dwarfs, cold balls of carbon floating in the dark. And even black holes, as we learned in our previous journey, will evaporate. They will turn their mass back into radiation. Ultimately, in the unimaginably distant future, all matter may decay. Protons may break down. The atoms that make up the rocks, the planets, and our bodies will dissolve into light. The universe will become a sea of photons, a bath of pure radiation cooling toward absolute zero, spreading out thinner and thinner as space expands forever. This is the heat death, or the big freeze. It sounds tragic, an eternal cold night, but there is a beauty in it. It is the ultimate equilibrium, the ultimate rest. Light began the universe, and light will end it. We emerged from the energy of the Big Bang, condensed into matter for a brief, beautiful moment to observe the cosmos, and eventually, we will return to energy. We will return to the light. But that is trillions of years away. We are here now. We are here in the golden age of light. We are here while the stars are still burning. We are here while the sunsets are red and the forests are green. We are here to witness the rainbows. And we are creatures of light in a very literal sense. The warmth of your blood is stored sunlight. The electrical signals in your brain are powered by chemical energy that began as photons hitting a leaf. Your vision is the processing of starlight. Even your consciousness, the light of the mind, is dependent on this flow of energy. We are the way the universe sees itself. We are the eyes of the cosmos. Without us, without eyes to see, does the rainbow exist? The physics exists, the refraction, the wavelengths, but the color, the beauty, that exists only in the mind. We are the partners of light. It paints the picture, but we provide the canvas of perception. So, as you lie in the dark tonight, remember the journey. Remember the photon struggling for 1,000 years to leave the sun. Remember the 8-minute flight across the void. Remember the scattering in the blue sky. Remember the leaf that caught the light and turned it into air and sugar. Remember the eye that caught the light and turned it into a memory. The darkness of your room is not empty. It is filled with invisible waves, heat from your body, radio waves passing through the walls, the gravitational pull of the moon. And even in the deepest black, there is the potential for light. The neurons in your visual cortex are resting, waiting to paint the dreams of the night. The sun has set, but it is shining on the other side of the world. The light never stops, it just moves. It travels on, and so do we. Thank you for listening to Dreaming Through Knowledge. May your rest be deep, your dreams be vivid, and your morning be bright. Good night.